Hi. Hi, everyone. So welcome to these sections. This session is about enabling the DPDK-SR-IOV for the containerized virtual network function with Zun. And just an introduction, my name is Hongbin Lu. I'm the project team lead of the Zun projects. And with me is Tang Yaguang. He's from Lenovo and working on the MFE research. And there's two other people in this presentation. They are Zhou Bin and Sun Li. So they are not able to come. So we are going to present these presentations. So the agenda of this presentation, first we will have a brief introduction of the Zun projects. And then we are going to focus on the MFE support in the Zun. And then Yaguang will talk about the performance benchmark testings. And then we are going to show a small demo and then the conclusions. So this is the diagram from the OpenStack user surveys that is in the April 2017. And according to the surveys, there are about 70% of the OpenStack users that are interested in using the container on OpenStack. And the ranking of container is on the top. But given the increasing interest of the users of using containers, what are the general question that people is going to ask is, what is the solution that is available? And in general, today, there are three types of solutions. So the first type of solution is to integrate the container with NOAs and use the NOA API to manage the containers. Example of that is the NOA Dockers or the NOA LXD. The second type of approach is to install a container orchestration engines, such as Kubernetes, on a set of virtual machines that is provided by NOAs. Example of that is the Magnums and QSPET. And the third type of approach is using the Zun, which is the OpenStack container service. So first, what is Zun? And this is a brief introduction that Zun is an OpenStack container service. It is an official project. And it provides an API to provisioning and manage container without manage any VMs. So it can deliver a container with speed and simplicities because it is possible to use a single command to start a container in a few seconds, and that's possible. And we are able to provide API to allow users to specify arbitrarily the number of memories separate from the number of CPUs. So you have the flexible to choose any combination of memory and CPUs. And this is different from NOAs, that in the NOA you need to choose a set of favor that is already defined. And finally, in Zun, we treat the container as a first-class resource. So as a result, you can use the keystone to provide a role-based access service in the level of individual containers. And the neutron pod is created and for each container, so you can use all the features in neutron, such as the security group, foreign IPs, and use it in a combination of containers. And you can use single volume. You can bind a single volume into containers, and that's also possible. So all these features is unique to the Zun project, and is not available in other services as far as I know. So another way to run a container is to use the NOA Dockers. And generally speaking, NOA Docker is to provide a driver for NOAs to allow users to use the NOA API to manage the Docker containers. And this approach is suitable for the use case that require to treat a container as a VMs. But in general, container is not VMs. They are set of operation that is specific to containers and not shared with a VM. And this is why we created a Zun project that has our own APIs that is designed for the containers. And another type of solution is use Magnums. So generally speaking, Magnum is a service that is provide an API for user to provision a set of virtual machines and install a COEs on top of the virtual machines. And eventually, the user can use the COE they provision to run the containers. And there's a pros and cons of this type of approach. This is because the resource model of the Magnums. In Magnum, a COE is a resource, and it belongs to a tenant. And Magnum doesn't allow a COE to share between the users or share a COE across all the tenants. And as a result, in Magnum, what you can get is the strong isolation for the containers, because each container belongs their own COEs. But however, it might lead to a problem that there will be a low resource utilizations. That is because a COEs is heavy, it taking resource. It takes a set of virtual machines that is for running the control plane server, the COE. It takes a few frame IPs, it takes a few single volumes. And if the user wants the COE to be HA, an additional set of VM that need to be created for redundancies. So if there's a cloud that has a large number of users and each user wants to create their own COEs, there will be a lot of COEs in the cloud and taking a lot of resource, and this is undesirable. So this problem is solved by Zun. And in Zun, we are using a centralized approach to manage the containers, but still make sure the container is isolated by tenants. And also, Zun doesn't assume the containers to run in the virtual machines. So you have an option to run the container on bare metals and to get better performance. So in Zun, the key concept is the containers. It represents a single containers. And you can create, update, delete, stop a containers. And there's a set of operations that is to relate to the networks. For example, you can attach a container to a neutral networks. You can add or remove a security group for the containers. And there's an event operation, such as attach to the terminal of the running containers, and execute a command of the containers and retrieve the output, and do a commit of the containers and upload the image to the grants. And this is what the container API is going to offer. And we are rolling out a new set of API that is called a Kasub. And Kasub is similar to the pod from Kubernetes. It represents a group of containers that is co-located, co-scheduled, and have the shared network and shared volumes. So this is the two key concepts of Zun. And for the architectures, we have a Zun API that is expose the REST APIs and manage all the compute nodes and schedule the container to one of the compute nodes. And we have a Zun compute that is an agent running on each node, and it manages a local resource, it manages the local containers, and checking all the compute resource that is in the node and report it to the API. And the Zun compute might talk to Cinders to do the Cinder volume attach, and it attaches a Cinder volume to the compute node to make the volume available for the containers. And Zun compute also talk to Neutron to prepare the resource for the containers. For example, create a Neutron pod. And in Zun, we specify the query as a driver as a network driver for the Dockers. So Docker will relies on query to set up the network of the containers. And query will use a Neutron for the networks. And this is a brief introduction of the Zun project. So I'm going to talk about do a deep dive of the Zun support of the MFV use case. So first, a brief introduction of what is MFV. MFV is a new way to design, deploy, and manage a network service. The idea, in general speaking, the idea is to replace the hardware with software. So there's a virtual function that is normally running on the dedicated hardware, special hardware. And in the MFV, we virtualize the hardware, virtualize the network functions and make it can run in any servers or in the VMs. The benefit of MFV is the network function can provision very fast, and it can be scaled up and scaled down in very fast. And the upgrade is easy. It can be relocated, and it reduces the cost to purchase a special hardware for the MFV and avoid the vendor lock-in. So today, most of the VNF is running on the VMs because there's a lot of support in NOVA that is provide the feature that is required for the MFV. And running VNF in container is not as common as VMs. But we see there's a potential to use the containers to run the MFV workload. And because there are several nice properties of the container that might suitable for the MFV use case. For example, the container can provision very fast, and it takes less memory. The package is easier to package because you can package the VNF as a Docker image and upload it to the Docker registry or Docker Hub for share. And the configuration is easy. So because in Docker, you have several options to configure the process that is running in the containers. And its portability is better because the size of the Docker image is smaller than the VMs. And the security VM is better, but because the container generally don't have the capability to have strong isolation between neighboring containers. But this can be solved by using an alternative container runtime such as the Queer containers, which provide the strong isolation capabilities. So right now we see there's a challenge of containerized MFV. And generally speaking, most of the gap is the support of the container ecosystem for the MFV feature is not enough. So for example, in MFV, it generally requires some features such as SR-IOV, CPU pinging, and the NUMA topologies. And these features need to be supported at the container runtimes. In addition, it also needs to support it by the container orchestration tools such as Kubernetes. And eventually, all these features need to be integrated with OpenStack and make them available for the OpenStack users. So we can use a Zun to reduce the gap of the containerized MFV. So in Zun, we are working on several features that is for the MFV. And the first feature we have implement is the support of SR-IOV. And so brief introductions, and SR-IOV is the standard to virtualize a PCI device and make it appear as a multiple PCI device. And most of the case, a PCI device is Ethernet controller. So we call it a PF. And it makes the PF appear as multiple Ethernet controllers. We call it a VF. So in Zun, we allow to pass through a VF to containers, and so that the container will have a better performance of the networking because it bypasses all the virtual switch layers from Neutron. So the step to enable the SR-IOV feature in Zun is first, as operators, the cloud operator needs to create a set of VF and then configure Neutron to run the SR-IOV agents. And in Zun, the operator needs to specify the whitelist, PCI whitelist, that to allow a set of PCI device to be passed through. And they also need to enable the PCI filters, which is the schedulers. It makes sure that a PCI request will schedule to a host that has a PCI device. And the last step is configure the queries to enable the SR-IOV drivers. And from user point of view, this is how they are going to create the SR-IOV containers. So first, the user needs to talk to Neutron to create a special port. That is, we call it a SR-IOV port. And this port is just like a normal Neutron port, but we annotate the port to tell the Neutron this is a special port and it needs to be passed through. And then the users, the second step is to talk to the Zun API to create a containers by passing the port that is already created. And Zun will figure out the port is a SR-IOV port and schedule it to the host that have the VF. And in Zun Compute, we assign a VF to a Neutron port and update the Neutron port to write down the information of the VF, such as the edges. And then we will call the Docker API to create a containers. And Docker will use use queries to set up the networks. And the query will retrieve the VF information from the Neutron port and do the corresponding Neutron port bindings and pass through the VF to the containers. This is how the workflow is going to look like. And then Yaguan is going to talk about the DPDK.
Okay. Hello, everyone. SR-IOV is already implemented in Zun for Zun to use so that containers can directly using the pass-through SR-IOV devices. And another feature is DPDK application to be run in containers. This is what we are doing some research so that to put the DPDK application to run in containers. So just a brief introduction to the DPDK is widely used by the NFV to improve the networking packaging processing performance. And because it uses the physical network card directly bypass the kernel stack, and it has some drivers of PMD. It's called the polling mode driver, which is used to move the kernel stack processing to the user space. For the physical hardware, it has RGB UIO and VFIO PCI kernel modules, which can the two modules can both could be used to use the hardware in the user space. And they also have the virtual hardware PMD drivers, which is virtual I/O user, which is a virtual hardware to be. This is mostly used when we run its DPDK application inside the VMs, and the VMs just have the networking hardware emulated by the QEMU. It also has a NetPcap PMD. This is an implementation of the kernel stack PMD. It uses the PCAP library to catch the raw data from the kernel networking stack. So we can see from the two graphs that how DPDK can be run inside the container. And the left one is DPDK applications run inside the container as a process, but it is using the VF directly from the host. So this we call it a user-land SRV use case. In this way, the DPDK application in container just using the host hardware. And in this way, we bypass the host kernel stack. And also in this way, we would get the best performance. So in this way, we can control how we manage the VF to allocate to the specified container. So this could be, there is a multi-talent issue. And we will talk it later. And the second in the right is the SRV in the kernel. So in this way, this is what now SRV is used in the Zun containers. As Hongbin just introduced before, currently we could pass through the SRV device to the container. In this way, the SRV, we call it pass-through, but it's not the same as the VM. When we said the pass-through to the VM is just directly put the hardware to the virtual machine as just a device just the same as the host. But in container, how Zun implemented is using the namespace to put the SRV device in the kernel stack to the container. So it's using the namespace. And we are doing some tests to see how we can achieve the performance. There are two cases we have tested. One is non-DPDK, just to evaluate how SRV in containers is better than the typical networking of the Zun containers. And the other one is using SRV and DPDK in containers from the kernel space and the user space. So here is the testing environment. And we are using 3 nodes, physical nodes of the Think Cloud, Think System server, and 1 controller and 2 compute nodes. They are deployed by the div stack. Each one with 10 gigabit networking card. So for the non-DPDK testing, I prefer 3 with different packet size to see how the performance of the package. And for DPDK application, we using L2 forward, which is an example, simple application in DPDK as the simple VNF in containers. Also, we're using the standard RFC testing 2544 to test the L2 forwarding performance. And for the packet generator, we use DPDK packet gen as the packet sending generator. So the first one is we compare Zun networking using SR-IOV and without SR-IOV. The first is without SR-IOV. This is what we have. We currently use without SR-IOV. When you use Zun to create a container or create two containers in the two computer nodes, the current way is a container is connected by the ETH pair through the to the bridge, and then the bridge will connect it to the OS. This is also the same topology of the VM for NOVA, and for the container is the same topology. The other one, and when using SR-IOV, here is the topology. In two computer nodes, we have each container running in each node, and the container is created using Zun and an SR-IOV port. Should be similar to the VM. We can see from the graph that here is a simple test result. We were testing using different packet size. We can see that when using SR-IOV in containers, the performance improved a lot, but it still can reach to the LAN rate. So this is improved the networking throughput compared to the current way. But for the NFV requirements, a LAN rate or nearly a LAN rate of packaging forwarding processing is a must. So we also did some SR-IOV with DPDK. So DPDK, when we running DPDK in containers, we did some tuning because DPDK is more complicated. There are a lot of tuning methods from the kernel, from the system, from the hardware. We have done, the tuning we are doing is following the DPDK official site. It includes setting the huge page size, which there are 1 gigabit or 2 megabit. So we are using the 1 gigabit to get the best performance. And for the NUMA, it's also one important thing to consider if you want to get the best performance. So the Ethernet card and the CPU for processing the DPDK application should be in the same NUMA. So you have to manually to do this. And in the further, we could using Zun to detect the physical hardware configurations. And another one is to isolate the CPU cores, which is used for processing the receiving and sending packages, which is normally is we allocate 1 core for the DPDK application. And the last, another way we have to do is to disable the CPU interrupts. This is one important, because even though we have isolated CPU so that this CPU core is dedicated to the DPDK applications, but there are the kernel also, there are still interrupts allocated to those cores. We just don't want to the cores to process those interrupts. So we have to disable the interrupt on those cores. For the DPDK SR-IOV, we are setting the two scenario testing. The one is user land SR-IOV used by the container. So in this way, the container is we have to manually to run the container because container requires the host resources such as the huge page and the root privilege to detect the hardware PCI info. So this way, we are not running the container by Zun. This Zun doesn't support to run containers like this. So we are running L2 forward inside this container, and the backend engine is running in one compute node, and the container to be tested running in another node, and inside the container L2 forward is running. So in this way, we are testing SR-IOV with DPDK, and the L2 forward, which is regarded as the VNF application to be tested for the networking forwarding performance. Another one is containers using SR-IOV by the kernel, which is currently Zun supported SR-IOV mode. In this way, we create a container and using the SR-IOV part. So this is what Zun could be used. So the container is created by Zun, and in this way, there's something need to explain that this is different from the what we're doing inside VM. So in this way, the SR-IOV part is still in the kernel namespace. So when we're running the DPDK application in containers to use this SR-IOV part is actually a kernel space interface. So the DPDK application can't use it as a user space device because the container we don't we have to use this device using the UIO module. It's not managed by the UIO module. It's managed by the kernel driver. So in this way, we are testing using the DPDK netpcap PMD driver. And the performance is as below. We put the three scenarios together. So one with SR-IOV without DPDK, and the other two is SR-IOV DPDK running in the user space. And the last is, the other one is SR-IOV with DPDK in the kernel space, which is we have to run container created by Zun and SR-IOV device managed by the Zun. So we can see the best one is SR-IOV DPDK in the user land running in the container is reaching to the length rate. Only the 64 BSS packet is now line rate. So this is what we expected, and we believe that using container in this way is approaching to the physical server performance, because containers just namespaces, and DPDK application running inside container is almost the same to be running in the physical server. And we don't need that much of the tuning for what we use in VM. So here is a demo to show that we could just click
okay,
the screen. So here is a small demo. Just we are using Zun to create two types of containers. One is just the normal container, and the networking topology is using OAS, and we're running a perf inside the container to get the performance of the container. So this is a regular port created by Neutron, and we can specify when running the container. And inside the container, we're running a perf. So we directly inside the container, and we can run a perf in the container to get a basic the networking throughput performance. We are using the UDP as the packet protocol. Because it's using the OAS as a bridge, it all goes through the kernel space. The performance is just around 2.68 gigabit. Then we would use to create an SR-IOV container, which is using SR-IOV part created by Neutron, just the same as we were using SR-IOV in Nova, just to create a direct type of port. So with the same packet size and just using the SR-IOV port, we get around the 5 gigabit throughput for the container using SR-IOV.
Yeah.
So what we are doing is just a research to see if DPDK and NFV applications could be running inside a container, and the container with SR-IOV for high throughput, apparently it's better than to compare with the OAS networking. So using hardware to get better performance. Also, in this way, the VNFs is managed by OpenStack components. It's automatically to allocate the available VNF to the containers. We have the schedule. We have clear to create and manage and using the VNF in the physical server. But in this way, as we from the test, we see that it's not best to run a DPDK application. It's the SR-IOV device pass through to the container is still a kernel space interface, but it improves a lot for the throughput compared to the OAS networking. To achieve the ideal performance, we could run DPDK and inside the container just using the SR-IOV device directly. This is what we call it the user land. In this way, we don't have to pass through the VNF to container because the application running in the container will automatically to detect the available VNFs in the host. So we have to require the root privilege to run the container so that the DPDK applications in container could get all the information it needs. So in this way, we got the best performance approaching to the line rate forwarding, but at the same time we satisfy the security and there are also other issues such as the multi-tenancy issue. So because the VNF we are using is not managed by any OpenStack components. When we run the DPDK application in container, we have to manually to choose which one is available or which one we want to use. So in this way, we have to manually to decide and to manage the available VNFs. Also, in this way, while requiring the root privilege, and this is so far, this is a must requirement so that DPDK application could be run inside a container. And I think, so here is what we are doing, and we are researching to putting the VNF inside a container, and I think this is possible. We're already making SR-IOV feature available for Zun containers, and it's nice that we may make a NUMA and huge page and CPU pinning to be available in Zun so that we can use Zun container with these features. It would be more easy to run VNF inside a container. So the benefit is compared to the VM, we could achieve the same or even better performance because we don't have the virtualization layer. We just use the namespace. So the performance should be same to the physical server. But at the same time, containers are managed by Zun and other OpenStack components. So in the whole architecture, the Vim is there is no big change to the Vim, but we may need a little change to the VNF manager so that it could using Zun API to create containers. Or it should be aware of they want to using virtual machine or the containers for specific VNF. So this is what we are sharing. Any questions?
I think we are running out of time. So if any question, you can ask me after. Thanks, everyone.